Algorithms are methods to solve different kinds of problems. There's all sorts of problems that come up in real life that need to be solved on computers. Some examples that come up in, well, why don't you come up with an example? Come up with an example that you think requires something that we call an algorithm. Who's got one? Sorting. Okay, sorting is like the ABCs of algorithms, right? You have to sort things. Every application needs to sort things. There's got to be ways to sort. And almost every algorithms class starts talking about sorting methods. And it also gives a very nice way of talking about how to measure algorithms, how fast they are, because some sorts are faster than others. There's also other different aspects to sorts that are neat. Some sorts, if the data happens to be very, very well sorted to begin with, finish early. Some don't. Some sorts keep data that have equal values in the same order that they came in, rather than randomly switching them around. Those are called stable sorts. Some sorts are sorted in place, using the same amount of space that the input was given in, rather than using a lot of extra space. These are all aspects that are important, but most of them are engineering and experimental aspects. So that's what this course is going to thread a line through. A lot of it's theoretical. We want the asymptotic complexity, the big O of an algorithm. But a lot of it is experimental too. This is an n-squared algorithm. It seems to run fast. How come? What are the engineering tweaks that are making it go? And there's a whole large interest in that aspect of algorithms as well. OK, another algorithm. Anybody think of any other one that they've ever heard of?
Travel. Like map, system travel, air travel.
Like traffic control.
But yeah, like putting flights together, map, getting.
OK, so you have a list of when flights have to be, where they have to be, and deciding what's the best order to do them in an efficient way. So that's kind of called a scheduling algorithm. That's a good example. Other examples. Let me give you an example. Would you call this an algorithm? You're building a program to play some game. At some point in the game, some of the colors get blanked out. So it looks like this: red, blue, green, blank, yellow, green, blank, yellow. And you're supposed to make this pretty graphics picture all shift down. Right? Now, most people wouldn't call this a problem that needs an algorithm because it's too darn simple. Nevertheless, if somebody who's a darn good programmer, who can see the big picture of object-oriented programming, who knows how to create sockets and listen for bytes, on a network stream, and even go ahead and create clients for complex things, still could conceivably carelessly write an algorithm to do this problem and have it be really inefficient. So here's a really inefficient way to do it. I'll look through looking for something that's not blank, and then I'll look through looking for the most bottom place that's a blank, and then switch those two. And now I'll go back to the top and do that again. All right, now there's a big leap between writing the loops out to do that and me just saying it. But that's the leap that I hope you can kind of fill in. Now, I know you might not be able to, and later on when I get to the real stuff in the notes, I'm going to have you actually write a little code with me. And when I'm completely convinced that it's boring and you can all do it and it's trivial, I'll stop doing that. But only when I'm convinced. Right now, I'm not going to do this. This is just an example I want to show you more abstractly. But that doesn't work so well because every time you go ahead and find a non-blank, you might have to look through the whole list. And then you have to look through it again to find the bottom blank one, and then you have to switch them. So every time you do this, it takes order n operations. And you're going to do it possibly order n time before you actually flush everything to the bottom. So it ends up being about order n squared. And that's really not the best way to do it. The best way to do this is actually to work from the bottom, move your way up. The first place you get to a non-blank, you shift it down to this spot. And then you keep a separate pointer pointing to the next open blank spot. And you keep going. And you move that to the next open blank spot. And you keep going to the next non-blank, and you push that to the next blank spot. I'm doing this quickly because most of you did this. You should probably have some recollection of, oh, I did it one way and it didn't work, and I spent a lot of time putting Band-Aids on it until it finally worked. The right way to do this is to carefully think it through, make out your, quote, algorithm, and make it in linear time. It should take time proportional to this list to collapse this. All right, I won't go through any more details, but that's an example of an algorithm, but one so simple that it doesn't require any particular technique. It just requires being a little slow and careful in your choice in your design at the beginning. OK. Any other examples of algorithms that you've ever heard of, problems that you need to solve that?
Shortest network. Given a random set of points, what's the shortest path that hits all the points, all the cities?
Okay, that's called minimum spanning tree. Right, so that's like your town gets flooded out. Big tidal wave. Whoosh! Town's gone. Okay, the water drains away. Now all the roads are mud, completely unusable, and you have to repave the town to use it. And the town looks like this. I'm going to make a point at every intersection. Here's Harry's ice cream store. Here's the post office. Here's who knows what. And here's the old roads that are now all flooded out. So why isn't this town a grid? Because it's like Boston, and it was built in 1600, who knows what, and the cows used to eat here, so the town is a mess, and you can't find your way around. But that's the town. It's flooded out, okay? Back Bay gets flooded. No more landfill. Goodbye. Whoosh! Here's a bunch of cities, or intersections, or places you want to reconnect. What's the minimum amount of gravel you have to put down to reconnect everything? All right? That's called minimum spanning tree. It's a tree because you'd never reconnect things here with a cycle, because here, let's say this is let's say that's the minimum. You'd never add this one in because these guys are already connected in. So you never have a cycle in this shortest subgraph that reconnects everything. It always ends up being a tree. Everyone understand that problem? That's a famous algorithm. We're going to talk about that sometime in the second week. There's lots of ways to do it. There's two different style algorithms. They both use the same greedy approach. This algorithm actually gets solved the first way you would think of solving it. If you gave this to an 11-year-old, he would guess the right algorithm. The right algorithm is take the very smallest edge and keep adding edges smallest at a time, making sure you never get a cycle. There's different ways to do that. In fact, it's a whole 2 hours to talk about it. So that's all we'll do right now. Any others you can think of?
Coloring the map.
Oh, there's a good one. Okay, so this is a graph again, and it represents a map where this is a region of the map, and an edge represents that there's a border between this region and this region. And you want to color the regions of the map, or the nodes, so that no two adjacent ones have the same color. So a very, I don't know, a random motivation for this is you're actually building a map and you don't want two adjacent things to both be blue. There's other more practical applications of coloring. But that's the way it's usually presented. So can you do this with three colors? Can you take three colors, color these nodes red, blue, green in such a way that no two adjacent nodes have the same color? All right, so you should know right off the bat that that's a very, very interesting problem to talk about from the point of view of how hard it is. If I draw a map on the board like this, which has no crossing edges, which is a planar graph. Remember what planar graphs are? It means I can draw it without crossing the edges. If I draw a planar graph, then there's a famous theorem called the four-color theorem. And it says that you can always do it with four colors. So if I put a planar graph on the board and I say, can you do this with four colors? You can just say yes. All right? And it's not such a hard algorithm. It's one line. You know, system print line, yes. I can do it. If I asked you, can you do it with three? Well, that's a little bit harder. If I give you a graph that's completely general and has crossing edges, and I say, hey, can you do this one with four? Can you do it with five? Can you do it with three? That's an NP-complete problem. And for now, what NP-complete means is that nobody has any idea of how to do it, and nobody ever will likely have any good idea of how to do it in a polynomial time way, in a fast way. The best way anybody knows how to do it is brute force that takes exponential time. How would we do this brute force?
Start trying.
Start trying. How many possibilities are there? This is why you need to know discrete math. How many different ways are there to assign red, blue, and green to all these different nodes? Let's say there are n nodes. You have three colors for each node. How many possible colorings of this map are there? Geez, great. That's right. If there were two colors, it'd be like binary numbers, right? 0, 1. So there's three. So it's 0, 1, or 2, n possibilities, 3 to the n. I know, relative to all the other hard stuff you must have done in discrete math, this is like a piece of cake, but still, you can easily forget.
You're coloring the nodes and not the...
We're coloring the nodes, right? So there's 3 to the n possibilities. So you could easily have your program run through all 3 to the n possibilities, see if any of them work, and report yes. And if you're really lucky or unlucky, it'll find out that the answer is yes on the second to last one. Right? So your algorithm will take 3 to the n minus 1 steps. And each step requires you to go through the whole graph and check whether any of the edges that connect 2 vertices, have 2 vertices of the same color. So it would be 3 to the n times how long will it take to go through the whole graph, proportional to the edges. So 3 to the n times e times the edges. That's a horrible algorithm. If we put in a map that represents, say, downtown Boston, where there would be, say, 500 intersections, so this would never finish during our lifetime. All right, so we got to do better than that. Just to give you a sense of how problems change, and this is really one of the coolest things about algorithms, and one of the things I want you to develop an intuition about, but I need to tell you that it takes sometimes years and years to develop this intuition, so we're going to pretend to develop the intuition at least. If I told you, I'm giving you a graph and I want to know, can it be done with 2 colors, yes or no? 2, no more, no less. Can you do it with 2? Tell me yes if you can. Tell me no if it needs more than 2. That problem is a polynomial time problem and is equivalent to determining if a graph is a so-called bipartite graph. If it can be split into 2 sides, the vertices on this side and the vertices on that side, with nothing but edges going in between them. That is, no edges in between the vertices on this side and no edges in between the vertices on this side. That means this would be the color 1 and this would be color 2. And all the edges just go in between. It is not hard to figure out if a graph's a bipartite graph. And you can do it with any number of the techniques we'll talk about next week. You can do it with depth first search, you can do it with breadth first search, and almost the first algorithm you try will work. You basically try to see if it can be done. You start with any node. If it's white, then make everything connected to it black. Make everything connected to those white. Make everything connected to those black, and keep going. And if you ever get a contradiction, you can't continue, the answer is no. And if you succeed, the answer is yes. How long does that take? Proportional to the edges in the graph. It's fast. So that's an easy problem. Hey, did I just get a problem that's NP complete, or did I just get a problem that has a chance? And you need to have a sense of the techniques that are available to you. You need to know the results in the applications relative to that field, and you need to be able to discern the frontier between very, very easy and very, very hard. So there's a bunch of ways to kind of organize algorithms. One way is by technique. And some of these techniques you know. There's recursion. This is taking a problem and thinking about it top down, splitting it into its subpieces, solving the subpieces, combining the solutions for those subpieces. Sometimes it's called divide and conquer. You've seen this many times. There's another style called dynamic programming. You've also seen this too. In the scheme course, they call this memoizing or memoizing. It means going bottom up instead of top down. And generally, it's used as an alternative to recursion when recursion tends to call the same subproblem over and over and over again. Here, you make sure you call each subprogram once by going from the bottom up and hoping that the total number of subproblems together is a polynomial number. We're spending a week talking about this. So if that didn't completely click in some idea you had, don't worry, we'll be back. There's another strategy that's often used called the greedy strategy. And this is basically a strategy that says, do the thing that locally seems to be the best and hope that when we're all done, it'll work out. What's an example of a greedy strategy? Like that bipartite example I just gave you. We want to figure out if we can color the graph with 2 colors. So pick a color for an arbitrary node, and then let's look at all its adjacent nodes and color them with the other color. That's a greedy strategy. We're just going to hope that it works locally, and then when we're all done, hope that it works globally. If we tried that same strategy for 3 colors, randomly picking 1 or 2 colors, not the original one we chose for the ones that were adjacent, and just kept going, we would have to backtrack. It wouldn't work. There would be no guarantee unless we actually went through all 3 to the n possibilities. So sometimes the greedy strategy ends up with a polynomial time algorithm. Sometimes it doesn't. As you might guess, there's a mathematical theory behind all these techniques. Recursion goes with recurrence equations. EQTS, equations, jeez. It goes with proofs by induction. Dynamic programming goes with queues and tables typically. Recursion goes with stacks. These are just associations you should make. The greedy strategy has a large mathematical theory behind it, which is way too complicated for this level course. We didn't even touch on it in discrete math. It's really kind of an upper level course that relates to this, but it's really cool, and it might be a nice topic for this class later, called matroid theory. There's a nice book by Lawler about matroid theory. I have it in my bookcase. It's a book all about which algorithms succumb to the greedy strategy and why, and a general theory about such algorithms. The example that we do in the greedy strategy is a minimum spanning tree example, which I mentioned before. And actually what Mike mentioned before, a scheduling problem, works with the greedy strategy too. So there's a number of really practical things. We won't talk about this at all in class. We'll talk just about the practical ways of implementing greedy strategy. Okay, a little aside before I keep going on with this intro. There's one really, really cool example of matroid theory that it's conceivable some of you actually had a connection with when you were kids. And I'll make a little picture here. And maybe on a recitation we'll actually go ahead and have time to look at this more in an advanced recitation perhaps. Here's a little graph. In the 60s and 70s, there was a game marketed in this country called Bridget. Anybody ever have that game? Not one person. All right. Well, my grandmother did. It's a game called Bridget. It basically was this game where they gave you a little board that looked like this, and you took little blue and red girders, or edges, and you took turns with your partner putting these edges in these various places. And the idea was for one person to make a path of, say, red from this vertex to this vertex, and for the other person to block that path using the blue ones. Does it ring a bell a little bit?
A different game called Twixt.
Yeah.
Twixt. Okay. So you've seen something like this. All right, so maybe that's the newer version of it. This is a really interesting game, and it doesn't seem trivial when you play it. It's not like tic-tac-toe where after a few weeks, oh, I don't think there's anything there. You can play this game a long time, and actually people feel they're better than other people. This is a completely solvable game, and it's solvable in polynomial time. In other words, if I give you a position in this game, you can run it on a computer program, and it will tell you the correct move to make if you can win. And it will tell you, I'm afraid in this position, no matter what you do, if the other person plays as good as he can, you will lose. It will tell you whether you have a winning position in that spot or a losing position. And if you have a winning position, tell you which is the best move. That strategy is based on matroid theory. It's based on intersecting spanning trees. It's based on something that comes up in a greedy strategy. It's a really cool, cool problem. It's called originally the Shannon switching game, named after Claude Shannon. Shannon did a lot of work in the 1940s. Claude Shannon was an electrical engineer and an early computer scientist and a brilliant mathematician. He did stuff in game theory. He did stuff in electrical circuitry. He did all sorts of cool things. He was the first person to describe how a chess playing program should work, and he actually wrote a program, I think, for, well, I'm not sure if he actually did it, but I think he might have actually written an early chess program. And he solved this game mathematically. All right, the reason I'm telling you this is because a very similar game is very hard and doesn't have any nice solution. And here's what the similar game looks like. Looks like a bee's nest. Let's make a few more just to give you a sense of this game. So you have this side, this side, this side, and this side. And in this game, you have two players, one with red pieces, one with blue pieces. And the red player wants to move from this end of the board to this end of the board, making a complete path. and the other player wants to move from this end of the board to this end of the board, making a complete path that goes from this end to that end. The paths can snake up and down as long as they make it from one side of the board to the other side of the board. If you think about this for just a few minutes, you'll realize that only one player can succeed in this goal. Making a path all the way from here to here precludes the possibility of a path coming down from the top to the bottom. It cuts it off. I could easily tell you, oh, this game is really just the same as this, and you would believe me. Okay, it's exactly the opposite. This game is a very, very hard game. This game is actually p-space complete, which, since you don't know what NP-complete means, p-space complete is just another buzzword, but it's even worse than NP-complete. Okay? It's bad, bad, bad. Nobody has any idea how to solve this game. This game is called Hex. H-E-X, for the hexagons. This is a really interesting game. You can have tournaments in Hex. People are good in it. It's a really cool game. This game is not interesting from a games person's point of view, because anybody who wants to play a game is often kind of a, I don't know, a money kind of a guy. Nobody is going to play this game because anybody who really cares about it will study it, memorize the strategy, do it in their head, and you'll never win. It's like playing tic-tac-toe. I mean, it's just not interesting. But that is an interesting game because it's computationally intractable. Very similar games. This is basically choosing edges. This is basically choosing nodes. And they're not the same. OK. Questions? Yeah.
You said, well, first of all, you've got vertexes in this hex game. You're traveling along the lines, basically.
No, no, no. Red, red, blue, red, blue, red. I win.
But essentially, it's really, if you think about it, it's the same thing, isn't it? Because each one of those hexagons corresponds to it's like a slightly smaller hex map if you're traveling along the lines. Anyway, that's not the point. You've got multiple destination hexes, right? Which is what makes it hard. Now, in the way that you can you move backwards and forwards?
In this game, yeah.
And in the other game, no? Or
in the other game, it's okay. If this is red,
yeah.
I color this red, and this is red,
Right.
and this is red, and this is red, red,
Well,
red, 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 red. If these were the red edges,
right.
and everything else is a blue edge,
Right.
then red loses.
Now, let's say if I were red and I was coming out, could I actually go back in the direction that I came from?
It's basically, think of it as just a whole collection of red edges. And if there's a path from here to here among those red edges, then you win. So you can think of an ordering, but it doesn't, that's just your own perception that there's an ordering. When you're all done in the game, there's going to be a bunch of red edges. If there's a path from here to here, then you win or you don't win.
You're adding edges all the time.
You take turns adding edges.
They don't have to be connected.
There is no back.
No, they don't have to be connected. You can choose your edges anywhere in the board. Right. It doesn't have to be connected to where you went to last. Right. And neither does it have to be connected here.
Right.
Right. Okay, let's. Okay, so one way to think about algorithms is a big, big, big topic is to divide it up into these techniques and study the techniques. The techniques, along with the basic data structures and then the fancier data structures that I will talk about in detail, let you do complete solutions to problems. You can't do complete solutions to problems just by having somebody describe a vague method like I've been doing right up till now anytime we've talked about an algorithm. I go, oh, you kind of do this and that. You've got to talk about how you're going to do it. The implementation does count, and it's important. Some of the basic data structures work pretty well, but you can soup them up with fancier ones. We'll get to kind of a middle stage as far as the complexity of data structures go. The other way to divide algorithms up into topics is to talk about the different applications. And that's what we started doing a few minutes ago. There's sorting and searching. Those are so fundamental, it's the first thing anybody thinks about. I've got a whole bunch of data stored. Somebody wants to search for something, change it, delete it, insert to it. That's searching. Sorting is you want to take that information and sort it up. That's one kind of application. What's another kind of application? Big, big style of algorithms we've been talking about. It's already come up a lot. Algorithms that are on graphs. Graph algorithms. This is a really, really fundamental and important part of algorithms. A lot of things are represented by graphs. And the most famous algorithm of all, which nobody mentioned up till now, is, well, I thought it was. Maybe it's not. But the most famous one that I thought everybody kind of heard of is what?
Traveling salesman?
Oh, it's a version of this, the traveling salesman problem. But I was thinking more of the flip side of that, the easier part of that, which is the shortest path problem. You're given a map. You go to MapQuest, right? You say, I'm going to Buffalo, New York. And you want to know the best route to get to Buffalo, New York. Well, it's a pretty simple kind of request. There's better be a way to do it. Otherwise, MapQuest isn't going to have much of a following. And there is a way to do it. And writing shortest path algorithms is one of the basic algorithms. And it's polynomial time solvable. The traveling salesman problem that Anthony mentioned is a famous, seemingly similar problem to that, but much, much, much harder, and it's NP complete. And that problem asks, if you have a bunch of different cities like this, the shortest path problem says, hey, what's the fastest way of getting from here to here? Assuming I know the distances, and the edges between all the cities. And they have weights on them. They tell me exactly the miles. Traveling salesman says, I want you to be able to go through all these cities exactly once. Visit every city. You're a salesman. You got to do some work there. And come back to where you started. And I want you to do it using the minimum number of miles on your car. Right? That problem is NP complete. That problem is hard. And actually, the hard part of that problem is not the shortest part of it. The hard part of that problem is just determining whether you can actually get through a graph. Let's say these are the roads. Can you get through this graph, starting from here, going through every node once, and get back to where you started? Well, in this case, the answer is clearly yes. That problem, remember what that problem's called? Anybody remember? It's got a name. It's called the Hamiltonian circuit problem. This problem is NP complete. What if you tried to solve this problem? What's the brute force method for solving this problem? Try each path. What represents a path? An ordering of the nodes, right? How many ways are there to order n nodes? N factorial. Okay, you can choose the first one. There's 1, 2, 3, 4, 5. There's 6 choices. The second one, there's 5 choices. Some of them don't make paths, right? So you're going to go through all these n factorials, see if they make paths. If they do, you'll say, I made it. And if they don't, you say, go to the next one. That's a horrible algorithm. That's the best one anybody knows. Remember this problem, Euler circuit? How's that one different? Right, instead of going through every node once, you want to go through every edge exactly once. Can you do that here? Can you start at a place, go through every edge exactly once, and end up back where you started? No, this you can't. This problem was solved by the mathematician Euler back in the 1700s, and it's a very, very easy problem to solve. Anybody remember how to solve it?
You have to have an even number of odd edges.
Parity of each of them.
Yeah, very good. You look at what's called the degree of the node, and if they're all even, the answer is yes, you can do it. If 2 of them are odd, the answer is you can start at one and end at the other and get through all of them. And if you have more than 2 odd ones, if you have like 4 odd ones, then actually if you have 4 odd ones, you can do it with 2 paths. And if you have 6 odd ones, you can do it with 3 paths. And, well, Euler circuit easy, Hamiltonian circuit hard. Shortest path easy. Longest path, what's the longest path? It's what's the longest way to get through from one node to another. That problem's hard. You know why that problem's hard? It's because Hamiltonian circuit's hard. Hamiltonian circuit is basically saying find if there's a path that gets through everything. That's kind of the longest path. The longest path is actually harder than Hamiltonian circuit. It's saying give me the biggest you can get. You can't even figure out if you can get all of them, yes or no, much less the biggest. So if Hamiltonian circuit's hard, certainly longest path is hard. I should say something. You might be thinking to yourself, geez, well, why is shortest path so easy and longest path so hard? You should be thinking that. You should be thinking that in every one of these pairs of problems. Why is this easy? Why is this hard? That's the intuition I want you to develop. But I want you to at least get the right idea for shortest and longest path. The longest path problem is hard. The shortest path problem is easy. But if I give you a graph like this, with negative weight edges on it. This can represent a lot of different things. If you think it's just bizarre, it can represent all sorts of things. This 3 represents, you know, I don't know, there's a waterfall from here to here. So I get 3 units of electricity moving from here to here. But I have to push the water up a hill to go from here to here. There's lots of reasons why you might have negative weight edges on a graph. But let's say you do, and let's say in this graph you want to find the shortest path from one place to another. If you have a negative weight cycle in a graph, then it's not even clear what a shortest path means. Right? You're not going to go round and round and round. That's not fair. So if I say, look, here's what a shortest path means in a graph that has a negative weight cycle. It means, what's the shortest path to go from here to here, but don't use any cycles. Just nice, normal path without cycles. The cycles aren't allowed. That problem is NP complete. Okay, remember that. It's not that shortest path is just easy by nature. It's easy because there are no negative cycles that might mess you up or you have to avoid. If you have to consciously avoid the negative cycles, the problem is very hard, and there's no way to handle it. That's why longest path is hard. Because longest path and shortest path are just the same thing, right? I mean, if I went ahead and took a graph with only positive edges and asked you for the shortest path, that's the same as turning all the edges negative and asking you for the longest path. So if I give you all negative edges in a graph and say, what's the longest path? You can do that problem. Longest path is hard because normally we're talking about a graph with positive edges. So there's a positive cycle. And we have to not use those positive cycles. That's what makes it tough. So be careful not to think, okay, I got the intuition. Short is easy, long is hard. Be careful. There's a lot of intuition to develop, and it takes time. All right, other examples. More graph examples. Somebody gives you a graph. They want to cut it into 2 pieces so that they go through the minimum weight edges, minimum number of edges. You can do that. That is part of a big fancy graph algorithm called maximum flow. We're not going to talk about this algorithm. It's very hard. Minimum cut, maximum flow, they're the same thing, and it's a hard algorithm. But you can do it in polynomial time. And as opposed to being linear, this one is typically n cubed. Not an obvious algorithm at all.
What are we trying to do here?
You're trying to take a graph, cut it into 2 disjoint parts, and minimize the number of edges in between those 2 parts. Okay? And it has to do with the same thing of how much flow can you push through these edges. The minimum cut is the same as the maximum flow. Let's move away from graph algorithms for a minute. Let's talk about the Electoral College. You got a whole bunch of numbers in a big, big bucket. They represent electoral numbers for the different states. And the question is, can you have a tie? Everyone understand the question? Can you pull out some of those numbers, add them up, look at the rest, add those up, and get the same number? Yes or no? Does anybody actually know the answer for the real Electoral College? It's an odd number. Is it an odd number? All right. So the answer is easily...
There are some states that could be split, Nebraska and Maine.
You mean the total's an odd number? All right. Odd number. All right. Half an odd number, still an odd number.
Only one difference.
Okay. So... Yeah, it doesn't matter. The general problem is NP complete. It's hard to take a bunch of numbers and determine whether you can split them into 2 parts and make the 2 parts equal sums. If I told you that every one of the numbers in that bucket is, say, limited to the number 10, everything is 10 or less in that bucket, you might have 8 10s and 33 9s and 58 7s. Because you got a big bucket, unlimited number of values, but each value is between 1 and 10, or any limited number, then you can solve it in polynomial time, as long as that number is a constant. So there's all sorts, and that method actually uses dynamic programming. So every algorithm has its frontier. Try to narrow down what makes it easy, what makes it hard, and that's what theoreticians sit and work on. this version's easy, this version's hard. You guys aren't going to do too much of that, but I want you to at least appreciate it from the point of view of the discipline. You're going to do more, okay, somebody's told me this is easy, can I make it happen? You're going to do more, somebody told me this is hard, can I convince myself that it's really hard by making the reduction and showing it's NP complete? Most of what you'll do is much more constructive. The real hard part is given something that's completely unknown and determining what the deal is. So I'll admit, I gave you one problem like that, but I'll tell you in advance. On one problem set somewhere, I said, there's an optional problem, here it is, if you're all done, try this, and write the best algorithm you can. The best algorithm anybody knows for this problem, as far as I know, is an exponential time algorithm. But nobody knows if it's really hard or NP complete or not. It may be that there's a good algorithm, but nobody's found it. So you're supposed to write one. The one you should think of is just any brute force one. You're supposed to analyze how long it takes and try it out and see just how slow it is. If you can actually think of a really good algorithm or use one of these techniques, then not only do you finish the problem set with an optional problem done, but you also become famous. Yes. All right. Here's another couple more examples. There's so many different pairs of these things. Here's a problem that came up before that you've seen. It's sometimes called the marriage problem or a two-dimensional matching problem. Somebody gives you a set of men and a set of women. Okay? Equal number. Say 100 men, 100 women. And they give you a list of pairs. In the pairs are one man, one woman, of pairs that are willing to marry each other. Right? So you got a whole bunch of pairs. By the way, if there's 10 men and 10 women, then what's the maximum number of pairs? You can, more or less? Yeah, what if I let everybody marry everybody else? 100. 100. All right.
Okay.
That's a trick question. You're out of here. Right. So I put in all these different preferences. And the question is, can I go ahead and marry everybody off without violating any of these preferences? Okay? That problem is polynomial time solvable. It's called bipartite matching. It relates, interestingly enough, to the maximum flow min cut problem. It also has around an n cubed or n 2.5 kind of complexity. And you can do that problem. It's called two-dimensional matching, matching up things in pairs. Now we go to Mars. Okay, we're at Mars. And in Mars, it turns out there was really life. But people, well, they're not really people. I guess they're Martians. So Martians group together sociologically in triples. Okay, there are 3 genders in Mars, A, B, and C. And you're given 3 sets, a set of A's, a set of B's, and a set of C's, say 10 each. And you're given a set of triples of people who are willing to form a union rather than pairs. Okay, so far, the same problem, just generalized to 3 genders instead of 2 genders. Expand your mind. You with me, Joe? Okay. We're in the 3-gender thing, that's why all right. Yeah. All right, what do you think? Can you do this problem or is it hard? It's hard, right. This problem is hard.
Is
right.
this a graph problem?
It's a graph problem. Although for 3-dimensional matching, it moves out of the graph area because a triple, for 3-dimensional matching, you have to model it with something called a hypergraph. And typically, it's just modeled by sets. You say, here's a set of A, B's, and C's, and here's a collection of subsets of size 3 each. So 3-dimensional matching, you usually describe it as a set problem rather than a hypergraph problem. That's a hard problem.
Is it similar to the penny problem?
Which penny problem?
I'm not going to do this, but where you see the optimal arrangement of pennies so that the most border.
No, I think you're thinking of the Steiner tree problem, which is a variation on the minimum spanning tree. And that problem is piece-based complete. But I don't think that, well, I should back up. All the NP-complete problems do relate one to another, but the relationships are not usually obvious. And that's what reductions are all about. So I answer your question, yes, there is a relationship, and I could take an example of your Steiner tree problem, as you mentioned it, or the penny problem, and convert it to a three-dimensional matching problem so that one is solvable if and only if the other is solvable. But that reduction wouldn't be so obvious. I don't think there's an obvious connection between the two. They're not exactly the same.
Okay, yes, but no.
Yes? Well, yeah, I'd say more yes. More yes. It's a good question. Okay, last example, then we'll move on to maybe some actual algorithms. In discrete math, you talked about logic. In how computers work, you talked about circuits. And you talked about Boolean algebra. And there were variables that were either true or false. And they could be negated or not. Pluses mean ors, and parentheses with separate lines mean ands. Okay, so this is product of sums, or conjunctive normal form. Can you put true and false values to these variables to make this whole formula true? In this example, for sure. Just set x true, and the whole thing's true. If I made this very long, made it 20 longer, it might not be obvious that you could form true and false variables and get the whole thing to be true. In general, the problem of figuring out, given a formula, is there a way to make it true by assigning true and false variables to the x, y's, and the z's, and the v's, and the w's, etc., that's NP complete, even if you have just 3 variables in every sum. If I knock it down to 2 variables in every sum, it becomes easy. And actually, it becomes equivalent to a problem that we're going to talk about in graph algorithms called finding strongly connected components. And it also has to do with a reduction. So we're going to talk about this problem much later on, maybe the last week of the course. The course is going to be divided up into 4 sections. This first week is intro, like today, along with let's get busy and talk about sorting algorithms. Let's talk about searching algorithms. Let's do a parallel review of discrete math and data structures. Let's go ahead and talk about some advanced data structures. Then we shift gears and talk about graph algorithms and geometric algorithms. Geometric algorithms are like what Rob mentioned a minute ago, but here's an example of one that's actually polynomial time instead of NP complete. Let's say somebody gives you a bunch of points on the blackboard or in a plane, and you want to figure out the border, or what's sometimes called the convex hull of those points. Imagine that these were nails nailed into the blackboard, ow, and then you take a big rubber band and snap it around all the nails, it would do this. These points are the convex hull. This is very useful. It gives you a sense of the border of a set of locations. It's used in many, many different places. It is the sorting of geometry algorithms. So we're going to talk about geometry algorithms. We won't get much into it. You can have a whole course at the graduate level just in geometry algorithms. We'll do just the convex hull problem. We'll talk about graph algorithms. We'll talk about minimum spanning tree, depth first search, breadth first search, strongly connected components, topological sorting. We'll do a lot more examples of that because that's more fundamental and even more widespread applications than geometry algorithms. That'll be the second week. Third week, we shift back and start splitting our focus not by the applications, but by technique. We'll talk about recursion versus dynamic programming versus greedy strategy and examples of each of those and how they work. And then we shift in the very last week to talking about NP-complete problems as a real topic. What does NP mean, really? What does NP-complete mean, really? And what do you learn as a person if you get a problem and you think it's hard, instead of just saying, I think it's hard because I really tried hard and I couldn't do it, how can you prove that it's NP-complete and thereby convince other people that it's probably not worth working on? We're going to talk about reductions and how they work. And then we're going to talk about, once you prove that a problem is NP-complete, how do you handle it? Approximation algorithms, probabilistic algorithms. Deal with the intractability. How do you do it? And a lot of that is some engineering techniques. There's a lot of work nowadays, a little controversial, but the idea of doing computations biologically. Representing a computation by setting up DNA in a certain way, letting the biological process go off, and when it's all done, you watch to see what the biological process has done, and that gives you an answer to the problem that you encoded to begin with. And you're leveraging the incredible parallel speed of organic material. That's really cool stuff. that goes beyond NP-complete because it's kind of using a different model of computation. Neil, you have a question?
I just had an intro question. When do you call something an algorithm and not? If you just want to like print out 10 numbers, you don't call that an algorithm.
I think it's a judgment call.
Some complexity about the problem.
Yeah, I think it's a pedagogy thing. If somebody's really worked hard and figure out how to traverse an array and print out the elements, and they're really proud of themselves, then you'd probably call it an algorithm. I'm really serious about that. I mean, if you try to publish something in a journal, then an algorithm is anything that solves a problem that nobody's solved before. So I think it's really a sociological question more than a definition. An algorithm is any method, including the simplest ones. Yeah.
Where's the line between algorithms and computer science? I mean, algorithms existed before computer science did. And now it all just seems to be computer science. All this stuff seems to be computer science. So have they just completely merged as a...
Oh, that's interesting. Well, if you ask Seth, he'll probably say that it's all not computer science, right? Is that true? I mean, don't pick on me. I'm just sitting here. No, Michael's question is like now algorithm seems to be part of computer science, and clearly it wasn't. I mean, Euclid's algorithm to find the greatest common divisor of two elements was described 2,300 years ago. I think, look, basically computer scientists kind of evolved from other life forms. If you look at the older, if you look at the older computer scientists, people older than me, look at the people who are the pioneers in the field, people in their 60s and 70s nowadays, where do they come from? They were mathematicians or they were electrical engineers. That's for the most part. You get an occasional physicist, but for the most part, mathematicians and electrical engineers. And they were dealing with mathematics that dealt with algorithms and all sorts of other things as well. And it wasn't really called computer science because what does computer science really mean? It means any kind of organized scientific discipline that relates to computers. So this stuff, now that computers came about, you can actually implement it. Suddenly it just gets sucked into computer science land. And I think it's true. I mean, I think it now is completely computer science. There's nobody who does algorithms who isn't a computer scientist. There are people who do recursive function theory who are not computer scientists. So that's a little further.
Procedural mathematics.
Yeah, procedural mathematics, I think, is all part of computer science. I mean, even discrete math. Look, discrete math wasn't a course per se 15 years ago. Nobody organized all that material, put it in one book, and said, this is one body of material. And even today, I mean, you all felt this way at one point or another. Maybe it isn't one body of material. Maybe it's just all 8 different topics, and what are they all doing together? You know what they all have to do together? The only thing they have to do together is that they tend to come up when computer scientists do real work. Every computer scientist needs to know all that stuff. So stick it all together. And then if you look a little more deeply, I don't want to be cynical because I actually believe there's a thread, but I think it takes time to appreciate it. There are similar themes that run through all those topics. And there are more and more general threads and connections between them, but it really takes some time to appreciate those connections. And maybe one day there will be more of a general theory that treats these things from a unified point of view. And nobody would be interested in it except maybe an academic, but still might be cool. Nobody mentioned this up till now, but I'll mention it now. And I'm sure you've all used these algorithms. You might have even thought about it yourself. But every application that you use, and I would really say almost every one, has somewhere in one of its pull-down menus a find in this page. Right? How does it do that? That's part of a more general algorithm called string searching. You give it a string, you give it a big bunch of text, basically another big string, and you look for the copy of the first in the second. How do you do that? If I gave it to you for homework, every one of you could figure out a way, and unless you had studied it before or you were told to try to do it very, very efficiently, you would probably do an algorithm that if the string was length n and the text was length m, you would probably do an algorithm that was proportional to the product of the two. I'll give you that algorithm right now. You'd think of it. Lay the pattern on the beginning of the text. See if it matches. Okay, if it doesn't match, move down one character. Right? How many of you would do that, right? I mean, it makes sense, right? You should do it. At least it works. There's no point getting an efficient algorithm that doesn't work. So at least it works, right? So you get the thing that works. You move it down a character. Every time you move it down a character, you've got to go back to the beginning and check for the matches. Every time you move down one character, you have to do n checks, the length of your string, of your search string. You got to do it all the way through the source string that you're looking at. It takes the product of n times m. N is your search, m is your text. You should know that for the most part, you can do this problem in time proportional to the text. It's much faster. Every string searching in any application you use uses one of these faster algorithms. How many papers have been written about this topic? Probably 300. There's lots of grad students out there. There's a lot of papers on this. It's called string matching. There's a lot of cool results. Some are very practical. Some are engineering oriented. Some are, I've got this really cool algorithm, and when I analyze it, it works this way, but when I run it, man, it's fast. And some are, I can get it asymptotically down 1 log n factor quick, even though in practice it doesn't seem to work faster at all. So there's different results. And it's a really, really important area because the thin line between experimental and theoretical really gets tested here. And you really want to do it. So it's a really cool topic, and it's worth learning. One of the early algorithms is due to Knuth, who's a relatively famous computer scientist, if not the most famous. Then there are some other ones that went from there, and it keeps going and going and going. Lots and lots of work in this area. We probably won't have time to get to it at all, but we might. We probably won't have time to get to the biological DNA stuff, but we might. But those are things that I'd like to do in parallel kind of in the recitations if we can, and take advantage of it if you're interested in these other topics. That's the end of the intro. Well, I guess not quite, but almost the end. There's 3 parts to every algorithm. One is somebody describes to you how it works and the data structures in some kind of abstract way, like I'm typically going to do every single day here. The other part goes more to the math side. Somebody's got some theorems or lemmas that prove that the procedures that I'm doing actually relate to the problem that I'm trying to solve. For example, if I choose the smallest edge to get a minimum spanning tree every single time, why does that give me the overall minimum spanning tree? I need a theorem that says that's true. You can still understand the algorithm, how it works without the theorem, but you want to understand why it works without the theorem. We're not going to spend too much time doing the why unless I think it reflects on the how. But you should know that behind every real algorithm is a theorem. Even the algorithms that just traverse through arrays and print them out. You can even prove that they work. It's a little pedantic, but you can do it. You can do it. You can prove that those things work. But the harder algorithms definitely need proofs. Those proofs are almost always proofs by induction. Okay, that's the general nature of computer science. The other side of the algorithm, the third side, is making the thing work, is implementing it. And that means taking the data structures, figuring out exactly how to make them, build them into real programming languages, running them, testing them, seeing if it actually works in the time that the theory predicts. Every one of these algorithms, once you've gotten these 3 parts down, needs to be analyzed, both theoretically and then you can analyze it all from an engineering point of view as well. We always have a big O complexity. We don't just measure and say that's our algorithm. We've got to do kind of both. And there's a lot of ways of analyzing an algorithm from the theoretical point of view. And in many cases, I'd say all the cases, these 3 different ways are motivated by the fact that the theory wasn't good enough to give us an interpretation of how things were really going on its own. So we kept adding more examples. Let me show you what I mean. The worst case analysis for an algorithm is the most common. We take the algorithm, we ask ourselves, what's the worst amount of time this thing can take? Say it has to go through all its possibilities. Say we never get lucky. That's the typical time complexity of an algorithm. We always care about that. We never care about best case. It just usually isn't important. Unless the best case happens to show up 98% of the time. But that hardly happens. Worst case is the most common. What happens if you have a really fast algorithm whose worst case, let's just say, is order n squared? But when you run it, it's faster than all the order n log n algorithms. n log n should be faster than n squared. But let's just say you have something that's worst case order n squared, and when you run it, most of the time it's beating these n log n algorithms. Well, what does that say to your theory? Your theory sucks, right? I mean, it's just not good. It's not telling you what it should be telling you. So it doesn't mean theory's bad. It means you need more theory. So in this case, you might notice, if you're a real good mathematician, that when you stare at the recurrence equation for this algorithm and you check what happens on the average, that you get a different answer than when you check what happens in the worst case. How do you do an average case analysis? This can be very complicated sometimes. But basically, it's just what it sounds like. You take all the possible inputs of your algorithm, you calculate the complexity for each one of them, you add them all up, and you divide by the total number of possible inputs. It's horrible, right? How can you do something like that? It's a mess. But the way you try to do it is you try to divide all the different possible inputs to your algorithm, say into, say, 3 categories. This category takes this much time, this takes this much time, this takes this much time, and you divide by 3. Or more typically, you split it up into, say, n categories, and you divide by n, where n is the size of your input. This case is actually not made up. This is a case from Quicksort. Quicksort's worst case is n squared. Quicksort's average case is n log n. And what's more, as far as the engineering and the details go, it tends to be faster than other n log n algorithms because of the constant factors. So even though the worst case said we'd never really try it, the average case justifies actually using it in practice. But it gives you the sense of the trade-off, the interplay, the relationship between the theory and the practice.
Do they look at averages in practice? Cases of real sample, real data?
Sure. People who really run algorithms do. There are actually academicians now who do experimental algorithm work. So they would also. They'd say, okay, well, we don't have any handle on this theoretically. Let's go ahead and see. And there's that too. This is a lot trickier. I need to describe this right now without a detailed example because the detailed example will get too long. I'll do a detailed example when we get to it, but I want to give you a sense of this because this is really cool. Let's say you have a data structure that lets you do the following things. It lets you insert, it lets you search, and it lets you delete. Okay, so these are the methods of your object or your data structure. Inserting, deleting, and searching. Searching will tell you yes or no. Inserting puts a new data element in. Deleting takes the data element out. And let's say you make this data structure up so that inserting takes constant time. Say you have an array and you just stick it on the end in the next available slot. Say searching takes, let's just say, log n time. And say deleting takes n time. It's a peculiar amount of complexities, but these 3 go together because these 3 algorithms need to be associated with that data structure. The worst case for this is constant. The worst case for this is log n. The worst case for the deleting is order n. Let's just say that's the way it is. But it turns out that when you actually go ahead and use this data structure, there is never a time where you get a lot of deletions relative to the insertions and the searches. It turns out that, let's just say, we have n times as many insertions as we do deletions. And a lot more searches than we have deletions. That means that even though the worst case here is order n, if we kind of think of them together as a group and we amortize the cost, we let the fast ones here balance out the slow ones here because the slow ones here don't happen very, very often, we might be able to compute that amortized over all 3 operations, each one of these is on the average order log n. It's not exactly the same as average, but it's very similar. It's not saying that the average of this particular algorithm over all the inputs is better than the worst case. It's saying the average of this still might be order n, but I'm splitting it over the time for other algorithms that tend to be run in a group with this one. It's taking the time for one algorithm and amortizing it over costs of the other one. I'll do a particular example of this later. It needs a lot of discussion. But be aware that there's an even fancier thing called amortized analysis that deals with situations that otherwise have no way to be carefully analyzed. All right, so now let's actually do an algorithm. Let's get down to brass tacks. Let's do one that you all, I hope, can do. No Fibonacci. Fibonacci is resting. He's still tired from discrete math. I will now do my imitation of Leonardo da Fibonacci. Somewhere in Italy. Okay, you got a bunch of numbers. You want the maximum of the numbers. How do you do it?
Remember the biggest one you've seen and look at the next one.
All right, so where are these numbers? Are they kept in a list in Scheme? Are they kept in an array in Java? Are we going to put them in a binary tree just because we're ornery? I mean, what do you want to do? Where do you want to put these numbers? Array is fine. All right, so they're in an array. They're sitting there in an array. You want the biggest one. So Chris's idea is, remember the biggest one you've seen so far. Well, I haven't seen a darn one yet because I haven't looked at it. So what's the biggest one I've seen so far? Oh, the first one will be the biggest one I've seen so far. Now remember that. Now what do I do? Go to the next one and compare it to the biggest one I've seen so far. If the biggest one I've seen so far is still bigger, just keep it as the biggest one. If the one I'm looking at is the bigger one, then make the biggest one I've got so far assigning to that, and continue in this loop. Can you all write a loop to do it? Yeah? All right, so I'm going to make you do it. It's going to torture me too. We're going to do it one time. I want to make sure. All right, so I'm going to write a little for loop for I starting at 0. All right, so how about big so far equals a bracket 0? Okay, biggest so far? And now I'm going to start this at 1. Fine.
We're writing this in math, or?
We're writing it in pseudo C.
I is less than length.
I is less a dot length. Pseudo C Java. Increment I. Do. If a brackets I is greater than big so far. Okay, it's too damn easy, huh? That's it, huh? Is that it? And then when you're all done, big, you return big so far. All right, tell me the truth. You could all have done this on your own without me doing it, right? I know it. All right. Your mother could do it.
Well, how do we know that A has any elements?
What? Oh, wait, oh no, I missed something.
How do we know that A has any elements?
Oh, yeah, well,
I don't like it all.
yeah, I don't know. I guess it could be empty, but let's assume it's got some. It's true. It's true that when you write any code, you got to test for everything. All right, fine. This is the maximum. How long does this take? N.
Is there a better way?
How many comparisons does it take? Let's count comparisons. N minus 1. All right. When you're talking about algorithms this simple, they're all order n. So I think it's worthwhile just to get a sense of how you deal with algorithms to talk about the specifics. Let's count actual comparisons because constant factors might matter here when you're actually doing it. And let's be very specific. So we'll count comparisons. We'll assume that's the slowest thing. And we have n minus 1. If I wanted to do minimum, how many comparisons? N minus 1. What if I wanted the maximum of a list and the minimum? I could do n minus 1 for the max, and then another n minus 1 for the min. That gives 2n minus 2.
Do the same.
But you have to make two
Oh, that's
comparisons.
true.
Well, actually, we could do that. Let's be careful. If I did n minus 1 comparisons for the maximum, couldn't I rule one out for the minimum? Well, as long as there was more than one element in the list, I would never have to look at that maximum again. I could just throw everything that wasn't the maximum into a new list, and this would be n minus 2. Well, so what? I saved 1. It takes 2n minus 2 or 2n minus 3. I'll write 2n minus 3 up even if we do that extra savings. And some of you are suggesting we do it at the same time, which is a good idea. We'll see about that and whether we can save a constant factor here. But before we do it, let's talk about doing this recursively, because recursion comes up all the time, and I don't want you to forget it. The equivalent recursive algorithm to this is one that says you've got an array of n elements, calculate the maximum from the second slot to the rest recursively, get an answer, and compare that to your first thing in the array, and output whichever one is larger. Everyone agree? What would the recurrence equation look like? Tn is the same problem with one less, plus one comparison at the end. If you solve this recurrence equation, and t of 1 equals 0, because if there's one element, you just return it, then you get the same old n minus 1. Right? This is the point where I stop. If we didn't do a whole month of discrete math, then we spend a whole week talking about these things. I'm not talking about them at all. I'm going to write them on the board. I'm going to explain where they come from. And if you don't remember how to turn this into t of n equal n minus 1, then Mark is going to happily review it with you. And you're going to love it. But that's the recurrence equation. OK. Let's think about a way to do the maximum minimum at the same time, which will do a better job than 2n minus 3. And we'll do this thinking recursively, because if you think recursively, it really gives you a tool that it's just so powerful. All right. Anybody got an idea? Here's a recursion idea. Well, let me hear your ideas. Anybody have an idea? Even iterative. Give me an iterative idea. Iterative or recursive to do max and min at the same time. If we just put another line in, but that's not going to do better than 2n minus 3. It'll work. Agreed. So can we do something better? Let me give you a hint as to why I think you should be able to do better. You're doing an awful lot of comparisons here, right? You're learning something about the numbers. It seems a shame that when you're all done, you act as though you've never seen those numbers before.
Divide and conquer.
You have an idea?
Break them into
What's the
two,
largest
have the
difference
maximum
between
and the minimum of the smaller ones, and then just compare the maximum.
OK, so let's consider Sam's idea. Let's break the list into two halves. Recursively find the maximum and minimum of each half.
And then just compare the maximum.
Then you compare the maximum with the maximum and the minimum with the minimum. So let's write this down. Tn is 2tn over 2 plus 2 half problem sizes plus how many comparisons when you're all done? 2 comparisons. Who knows what that ends up being? T of 2 is 1. There's 2 values, you just do 1 comparison. Does anybody know?
It's like a log n kind of.
Is it?
Yeah.
I think without the 2 it would be a log n kind of a thing, Tony.
Wasn't it?
Because it's doubling and halving at the same time, so it's a little tricky.
Well, then doesn't it end up just being?
Well, I'm going to leave this for you. I'm not going to do it right now. And since Sam thought of it, he can actually calculate how good his algorithm is by solving it. Maybe he's already has. But let's leave this for now. I'll leave it for Mark. He can do this in recitation.
Is that the right equation, though?
I think it is.
Because you're saying that you're splitting it in half and doing both max and min?
Yeah. So we have 2 halves. Tn over 2 is the time to do each half.
Okay.
So I got 2 of those. And then when I'm done, I have 2 comparisons left. I think it's right. Isn't it right, EJ?
Okay, your Tn is the double comparison. Okay, I'm sorry. Go ahead.
So this is Sam's method for doing max min. And it may be better, it may be worse, because I'm not telling you what the recurrence equation turns out to be. By the way, don't use the master theorem to figure it out, because that just gives you, it'll just tell you that it's order n. Well, duh. We want to know if it's better than 2n minus 3. So you're going to actually have to substitute here and see what you get. Maybe it's better, maybe it's not.
If you just did the maximum, would it just be +1?
Except if we just did the maximum, this would be +1. Yes. If we did the maximum with Sam's method, It would be exactly the same except a plus 1. No, it would just be, yeah,
Yeah.
a plus 1 at the end, right.
Minus 1 though.
Exactly.
So you can do both of them just with plus 2?
Sure. That's recursion.
You don't have to take it, you're doing both the max and the min and the chance?
You are taking it into account. That's what you get with recursion. The problem is defined in terms of itself. So you're doing more each time, but you're doing more in terms of doing more. So this is the only thing you pay.
So you do the maximum and the median and
If you figured out a way of taking the two medians and figuring out the actual median, let's consider Neil's point, because it's a really good point. And I think you all should ask yourselves the same question he's asking. Neil feels this is magic, if I can paraphrase your emotions for a moment. No, it's a really good point you're asking. He feels like, well, how do I get away with this? If this was just maximum, I do the 2 halves, max on each half, compare them with 1 comparisons, and this would be a 1. But now I'm doing max min. I seem to get it all for free. All I have to do is when I'm all done, I get a min and a max and a min and a max. I compare the 2 maxes, compare the 2 mins. That takes 2 comparisons. I'm all done. And I said that's exactly right. That is magic. What if you wanted to figure out the median this way, the center number? So I take 2 halves of the list. I figure out the center of each one. How do you figure out the center of the whole list having the centers of each half? I don't know anyway. So I'm going to write down infinity. Half joking, but there is a way. But maybe this way, if this way actually takes time n, then we're dead. Then we move this up to n squared. And n squared is way too slow to find the median. So the answer is it is magic, and the magic is here. The magic is in the connecting of the subproblems. And if you pay very little there, then you're safe. But the first part of getting the subproblem answer is free. That is free. Getting the 2 medians is free. What you do with them next, you got to be clever. All right, let's think of a different way of doing this min-max, which I think is a little bit easier to analyze than this, but very similar in style. Instead of doing things one by one, we're going to do things a pair at a time. So we'll take the first 2 values, and we'll set the bigger one to the biggest so far, and the smaller one to the smallest so far. Okay? Now we could do that and just go through the list one at a time, doing a double comparison each time. Compare this to the biggest so far, and if it's bigger, change it, and then compare it to the smallest so far, and if it's smaller, change it. And that wouldn't change the algorithm at all. But what can we do to make it better? What if we keep going in pairs?
And if you make a change in one, you don't even have to look at the other.
Well, that's true. So let's say we go in a pair and we figure out the max of the pair and the min of the pair. We know which one is bigger, which one is smaller. That takes 1 comparison.
Yeah, then you compare the max so far, the min.
Compare to the max only to the max so far, and compare the min only to the min so far. The min will never replace the max so far, and the max will never replace the min so far. This is essentially what you were saying a minute ago, but takes active control over which question we save. Let's analyze this. We're doing it recursively. We want to solve a problem, max min, for a whole list of n elements. Take away 2 of them, and get the max min for everything except the first 2. Okay? That's Tn minus 2. Now, how do we connect the answers together? You got 2 left over. You got the max and min of everything except those 2. Take your 2. Calculate which one is bigger, which one is smaller. That takes 1. Compare the max to the biggest so far that you got from recursion. Compare the min to the smallest so far that you got from recursion. And that takes 2 more. Now look at the original recurrence equation that we had. It looked like this. This is for doing max min without anything clever. 2 comparisons, going down 1 each time. When you finish with this, you get something about 2 times n. 2n minus 3 if you count the little details, but about 2n. What are you going to get when you finish this?
3 halves n.
About 1.5n. You're adding 3, but you take away 2 every time. So how many times can you take away 2 till you get down to n? About n over 2 times to take away 2 till you get down to n. And you're adding 3 every time. So this ends up being about 3n divided by 2. About. You can calculate the minus 1 here precisely if you go through it. This is a good deal faster, constant factor-wise, than this. If you were doing this on a billion things, you would certainly use this way. In fact, you wouldn't even do it recursively on a billion things. You would take this recursion, it's really tail recursive, and you'd iterate it. You can do this iteratively. Just a pair at a time. Go a pair at a time, calculate their max min, ask 2 questions. Next pair. I described it recursively, but there's nothing particularly recursive about this. It's really tail recursive, it's really iterative. All right, questions about this? These are all order n, but it's giving you the flavor of how to take what you're given and leverage it to the absolute max and knock down your complexity as much as possible. Are there questions about this so far? Okay, I want to do one more thing before we quit. Similar to this. Top 2 biggest. Now I don't want the maximum minimum, I want the top 2. One way to do this is to do just what we did with maximum minimum and get 2n minus 3. The slow way. Figure out the biggest, then figure out the next biggest. But the biggest is already removed. The biggest takes this much. The next biggest takes only this much, because the biggest is out of the list. That's one way. I'm going to describe another way in just a second. Before I do, I have questions for you. I said here, and I know it's just a matter of minus 2 or minus 3, but this is an implementation detail, and I want you to think about it for a second. I have an array. I'm going through an array. I find the biggest. And I say, well, the second biggest can't be the biggest, so the next time you go through, you don't have to look at that guy. How do you make sure you don't look at that guy? Here's a bad way. Remember what the value of that one is, and every time you go through the list, see if it's that one, and if it is, don't look at it. Right? That's horrible. You just did twice as much work as you did before, and you already looked at it. I'm only half joking. It's really easy to describe an idea like this that seems, oh yeah, well sure I'll do that, and then only to get back to your chair and go, I don't know how to do it. So how do you do it?
Take it out of the list, not ready.
How do you take it out?
Well, if it's on that chair.
Depends on what the data structure is that you're storing it in.
That's true. It depends on the data structure. We have to decide how we're storing this thing.
We're taking the largest one out?
Well, we have to decide what we're going to do. We have an array of numbers. We calculated the biggest, and we want the next phase that calculates the next biggest to take one step less, because presumably we won't be looking at the same n minus 1 numbers. We'll be looking at only n minus 2 numbers. And I'm asking, how do you really do it?
Well, if we
Yeah, Seth? Okay.
take the biggest element of the array and swap those 2 numbers and don't go with one.
Okay, good. So once you've found the biggest so far, all we've returned here is the actual value of it. What do we need to do in order to do Seth's idea? We need to say where it is, right? So we should modify our routine. We'll say location equals 0, and here location equals I. We'll remember where it is, not what it is. Is that what you're suggesting? And when we're all done, we take that A brackets I. Oh, not I, Jesus. Yeah, A brackets location. We take A brackets location, and we swap it with A bracket 0, say, and our next loop starts at 1 instead of 0, or starts at 2 instead of 1. I mean, Seth's a good idea. Seth's a good engineer. It was right in his head. Good.
Doesn't it take one additional step to label each of these numbers?
It takes a lot more than one each step, but we're only counting comparisons, so it's okay. Sam's got a good point. There are real trade-offs between, doing things like this and saving it one step later on. You have to decide what you're really comparing, and you have to do tests. And it's a really good point. But my point in this question is much more, do you see at least a reasonable way to do this so that it's not just, talking abstractly? And you should try to always think about that. Now, I want to go through this algorithm for top 2 biggest, then we'll quit for today. Then lunch. Lunch is on me. Diet Cokes for everyone. Here's another way to do the top 2 biggest. The analogy to think of is that you're having a tournament. Here are the numbers that you're going to find the top 2 biggest of. The top 2 biggest are 8 and 7. But think of this as a tournament where the numbers represent how good somebody is. So that if Mr. 8 plays Mr. 1, Mr. 8 is going to win. Just like you're comparing numbers, but these are players. One way to do the top 2 biggest, in a completely different way than 2n minus 3, and this only works with top 2 biggest, it doesn't work so much for max min, is to imagine that you're having a tournament. So that these 2 play, and these 2 play, and these 2 play, and these 2 play. And you get winners. You get 8, 6, 7, and 5. And then these 2 play, and these 2 play, and that's 8 and 7. And then these 2 play, and these 2 play, and that's 8. Okay? Everybody see the tree? You can do this recursively and kind of make this tree happen behind the scenes. You can do it iteratively and make the tree happen. Michael?
That may not necessarily work, because if you're going a bracket like that, what happens if you switch the 4 and the 7?
Yeah.
Then you're screwed, because the 8 and the 7 are still the biggest.
Oh, I didn't get the top 2 biggest. I just got the biggest this way. I just got the winner of the tournament.
Okay.
I'm not saying the second biggest is here.
Okay.
And you're right, it doesn't have to be. It turns out to be here because I stuck it on the right side, like you said, because I seeded this tournament out. But what if I seeded it badly? We'll get to it. We haven't gotten to that yet.
All right, but once you've broken them down into pairs,
Yes?
then the second biggest has to be either one of the top or the second one to the top. That is, it has to be 8, 6, 1, or 8, 6, 7, 5, or 4.
Good. And let me say what it is more generally. Good, and this will answer your question. Where can the second biggest be in this tree? Well, let me tell you. You were in this tournament, right? This is the easiest way to understand this. Think of yourself as in this tournament. Okay? What's the chance that you're the second biggest? What had to happen for you to have any chance to be the second biggest?
You're either on the second row or you lost to the biggest.
Lost to the biggest, right? If you lost to somebody who isn't the winner, you're not the second best. The only chance you have of being the second best is that you actually played that winner and lost. Because if you didn't, then there's somebody who beat you, who was beaten by somebody, or he himself, who actually did play the winner and lose. And that means you're not the second best. The only way you can be second best is to have lost to the winner. I'm going to circle that. This could be the second best. This could be the second best. This could be the second best. At every level, there's one possible second best. Everyone agree with this? Imagine yourself in a tournament. Imagine you're really good and you did really, really well. You thought you did super, but if you're not Mr. 7, Mr. 6, or Mr. 4, you got no claim to fame here. That means somebody else who beat you lost to the winner. And you're not second best. You're third or fourth, or maybe you're last. How many different possibilities are there? I started with 8 things. There's 3. If I started with 16 things, there'd be... And if I started with n things, there would be log n. LG stands for log base 2. Let's calculate how many steps this takes. How many steps did it take to get the biggest? 1, 2, 3, 4, 5, 6, 7. One less than the whole element. Why is that? Remember that the number of leaves, that the number of nodes in a tree of height n is exactly 2 to the n minus 1. Here the height is log n. So if you add it up, you get n minus 1. All right, I'm referring you back to your discrete math teacher. If you don't know that, then he goofed up. n minus 1. n minus 1 comparisons to move up this tree. Mark will teach you if you don't know that. Plus, what's the next stage? You got log n possibilities. You got to find the maximum in that list. So log n minus 1, just like we did before. The total time is n plus log n minus 2 in comparison to 2n minus 3. Who understands this algorithm so far? No one?
Where is that one, log n minus 1?
Because I have 3 left, I take the first one as my biggest so far, and then I look at the rest. Whenever I have a list of n things, I only have to do n minus 1 stages to find the biggest. So just log n minus 1. The same thing we did at the very beginning with the max. All right, so again, have the tournament run in pairs, have the winners play the winners until you get a biggest one so far. That takes n minus 1 steps. How many levels are there in a tree that's complete like this? Log base 2 of n. We run through that to find the max, and it takes log n minus 1 steps. The total is this. Yeah, Chris?
Of course, we're not paying attention to what the computational overhead might be to keep track of these.
We're going to do that in a second.
Okay.
And then I'll really let you go to lunch. But first, look at this. Which one of these is better?
For all the tiny n.
This is n plus n minus 3. This is n plus log n minus 2. Log n's a lot less than n. So this is better. It's better almost all the time. Maybe when n is 1, it's not better. Because this takes negative 2 steps when n is 1. You only do this on elements of bigger than 1. If it's 1, you just return, I can't do the problem because I need 2 to do it. So I think this is always bigger for n greater than 2. This is bigger than this. So this is a better method.